this video, we will derive a power function. To complete the proof, we need to first follow the pattern below to create a general form of the expression. A to the power of 1 minus b to the power of 1 is a minus b. A squared minus b squared. This can be factored as a minus b times a plus b. A cubed minus b cubed. Difference of cubes. This factors to be a minus b times a trinomial with a squared plus ab plus b squared. A minus b. This one will be times a quadrinomial. The powers inside of here will follow the pattern. A to the power of 3, right? We're going up by 1 each time. A to the power of 3 times b to the power of 0 plus a squared b to the 1 plus a to the 1 b squared plus b cubed. If you would like to check that, you can distribute it. So the pattern that we're building is that each time we can factor out an a minus b, and then we have to multiply by some polynomial. So we'll start off with a minus b, and that's being multiplied by a polynomial. We want to refer to each of the exponents in terms of n so that we can create a general form. The power that is inside the second quantity, is 1 less than the original power. So we're going to call that the first term, a to the power of n minus 1, plus a descends as b ascends, so this would be a to the n minus 1 plus a to the n minus 2, okay, it's going down, and now b pops up, okay, before b was 0, now it's b to the 1, plus a to the, subtract another 1, a to the n minus 3 times b to the add 1 squared, plus, and we don't know how long this goes on for, right? This n could be a to the 100 minus b to the 100. Yikes. So we'll put plus dot 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 plus. This is the actual notation for it. You put plus dot 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 plus, and then the form your final term or your final two terms will take. A is to the power of 1, and then b is to the power of 2, which is 2 less than the original, so b to the n minus 2, plus our final term, which is b to the power of n minus 1. This is very similar to binomial expansion, the binomial theorem, Pascal's triangle, except we have kept a minus b factored out, and we'll see why soon. Okay, so this is the general expansion of any quantity a to the n minus b to the n. Please keep in mind a to the n minus b to the n is not the same as a minus b to the n. So like I said, it takes on similar characteristics to binomial expansion, but it is not the same. Find the derivative with respect to x of x to the power of n. Here is my limit. This is what they're referring to as f of x when they write it in this form. They're asking for the derivative with respect to x of x to the n. So we're going to find the limit as delta x approaches 0 of, instead of x, you'll input x plus delta x. So if x is to the power of n, then the entire quantity x plus delta x will be to the power of n minus x to the n, your original function, all over delta x. All the expansion that we did above is to help us expand this. I have something to the power of n minus something else to the power of n. To visualize the expansion, I have named the first term a and the second term b. When I expand, I'll still use x and delta x, but this will help me follow the formula I came up with above. The limit as delta x approaches 0 of a to the n minus b to the n is equal to this whole thing. A is equal to x plus delta x. Minus b. Again, every time you see a in the general formula, you're going to plug in the quantity x plus delta x. Every time you see b, you're going to plug in x. X plus delta x to the power of n minus 1 plus x plus delta x to the power of n minus 2 times x to the power of 1 plus the quantity x plus delta x to the n minus 3 times x squared. Okay, and we don't know how many terms are in between, so we're going to just write plus dot 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 plus, and I'm just going to write the last term, which is b to the n minus 1, and b is x here, so x to the n minus 1. This is all over delta x. In this first quantity, we actually have x plus delta x minus x. Hey, x minus x is 0. This quantity that was being multiplied by this long expansion is now just one term. It's just delta x being multiplied by this expansion. That really helps us because we will be able to reduce delta x over delta x and no longer get an undefined expression. Delta x over delta x is a special form of the number 1. We are left with the limit of no longer a rational expression. At this point, we can direct substitute. So anytime you see delta x, we're going to plug in 0. Obviously, adding 0 to x does not change it, so we can simply take out all the zeros now. So instead of x plus 0 to the n minus 1, we'll just have x to the n minus 1, and then x to the n minus 2 times x. Wow, okay, a lot of stuff, a lot of x's here, but remember that when you multiply, you can add the powers. So when you multiply the same base of x and x, all you need to do is add their exponents. N minus 2 plus 1. That's just n minus 1. You have the same base. Go ahead and add your exponents. N minus 3 plus 2 is n minus 1 plus x times n minus 1. Hey, now we just have an innumerable amount of x to the n minus 1s. How many of those? We actually have n number of x's to the n minus 1. That is the derivative of a power. This is called the power rule, okay? It's a huge thing. So the derivative with respect to x of a power is equal to n times x to the power of n minus 1. And the power rule helps us with many things, with radicals, with fractions, with powers. Let's do some examples. The derivative with respect to x of x to the power of 5. N is our power. That will now become our coefficient, 5, times x to the power of, we started off with 5, so 5 minus 1. That is equal to 5x to the 4th. Now, whenever my mom would teach me this or refer to this, she would always say, pop down, power down, pop down, power down. Okay, so let's try that for something else, like x cubed. Pop down, power down. Pop the 3 to the front, subtract 1 from the power, and you have your derivative. The power rule. So convenient. Wow, so much faster than using limits, right? These shortcuts are going to come in super handy. First of all, we're going to rewrite 1 over x. This is 1 over x to the 1, but anytime, if I don't want it to be in a fraction form, I can rewrite it as x to the negative 1, meaning it's on the wrong side of the fraction bar. It was in the denominator. So the derivative with respect to x of x to the negative 1, we can use the power rule because it's a power. Pop down, power down. Bring the negative 1 down to be your coefficient. Negative 1 times x to the, and then you subtract from the power. Subtract 1 from the power, that is negative 2. Don't forget that you should not have any negative exponents when you're done. So we have negative 1 times 1 over x to the positive 2. Combine that so it looks nice and neat. Negative 1 over x squared. This is the derivative of 1 over x, or x to the negative 1. Our last power rule example is the derivative of the cubed root of x. We can actually rewrite this. Remember, radicals can be rewritten as fractional exponents. So square root is 1/2, cube root is 1/3. Pop down, power down. Bring 1/3 down to be your coefficient, and then subtract from the power. 1/3 minus 1. 1/3 minus 3/3 is negative 2/3. We can simplify this, and we should. 1 over 3 times 1 over x to the positive 2/3. Oh, but a radical in the denominator is a problem. First of all, I'm going to show you how you can write the answer with a radical in the denominator, how I will accept it, and then how to rationalize that as well. I'll show you both options. So the derivative with respect to x of the cubed root of x is equal to 1/3 times 1 over, this denominator is your root, so cubed root x squared. Combine those fractions, 1 over 3 cubed root x squared. I will accept this as an answer for your derivative, and I will also accept the rationalization, which looks like this. 1 over x to the 2/3. We need to multiply this by something that is going to result in 3 times x, so x to the 1. 2/3 plus what gives me 1? That would be 1/3. So we're multiplying by x to the 1/3 over x to the 1/3. That gives me x to the 1/3 over 3x. This is the other way you could write your derivative.